some further discussion. And application of logistic equations. Yeah. Modeling population growth. Yeah. So this equation is related to population. When we study population growth, yeah, we need to use some model, right? Yeah, we need to use some, ODE to model the population growth. Yeah. So this equation is pretty good in modeling population growth. Yeah, yeah. But the form is slightly different. Yeah, you can see these two forms similar, right? Yeah, because you just choose appropriate capital A, capital B. Yeah, yeah. But people like to write this form. Okay, this form, because there is a meaning here. Okay, there is a meaning here. Yeah. Well, you see this form. Okay. All right. Capital P function, the population size, yeah, as a function of time t. Yeah. The rate of change of the population function equals some constant r times the population at that time, yeah, then times another special factor, 1 minus p over another constant k. Okay? All right. Yeah, sorry. Yeah. So here, I need to discuss a little bit. Yeah. All right. Look at this form. Yeah.
You're saying that's a good application of the logistic equation. Like it always can provide the population growth.
Yes. So, we can say it in this way. This is the modeling ODE for the population growth, and it is a special case of the logistic equation. It's a special case. Yeah. Logistic equation can cover more than that. More than that. Yeah. But in this special form, that's the, on this question. Yeah. All right. Now we want to understand the meaning here. Okay? If it makes sense, right? Yeah, we want to see if it makes sense. Yeah. Let's look at the meaning of this. Yeah. Because how did people come up with this ODE to model population? Yeah. So based on the specific meaning here. Yeah. The rate of change, yeah, proportional to the, but if it's proportional, people feel not quite right. Yeah, because first, yeah, people model this population growth using this symbol, ODE. Okay, know this big parenthesis. Okay, yeah, yeah. But based on the statistics on the real world, populations, okay, statistics, it's like not that. Okay, so if you think about it, if you remove this big parenthesis, then the population growth function should be an exponential function, right? Yeah, and keep going. Yeah. Then exploded. The population, unlimited, no limit, exploded on Earth. So this population can be applied to animal, species, difference, human population. So all, okay, yeah, all populations. Then, but based on the observation of the real world, so any population, it looks like there is some limit. Yeah, cannot grow forever. Okay, yeah, no population can grow forever. Sooner or later, hit some bound. Okay, yeah, yeah. Then probably population, going down. Okay, yeah, going down. So yeah, so Then, in order to describe that kind of up and down phenomenon, so it's not enough. So another special factor should be used to reflect that up and down phenomenon. Okay? All right. So then, sometimes, people try different ways. Then, sometimes they come up with this one, 1 minus p over some constant. So look at that. If p is less than certain constant, this k constant, something like some upper bound control parameter. Okay? Certain constant, that constant is used to control the upper bound. Okay? All right. Think about it. When p, population, keep growing, sooner or later, it hits some upper bound, capital K, 1 minus p over k, when p equals k equals 0, right? If equals 0, derivative equals 0, that's going flat, right? Going flat, because derivative equals 0. So your population keeps the same. Okay? Yeah. All right. But think about it. If your population grows more than k, then this 1 minus p over k is negative. Negative, that means your derivative is negative. Negative, that means your population must be going down. So if your population is larger than that constant k, then there is some force, okay? Because the derivative is negative, so there is some hidden force. It forces this population going down. Okay? Yeah. 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 So then, but when p is smaller than k, 1 minus p over k is a positive number. So the derivative is positive, keeps growing. Okay? Yeah? If p less than capital K, then population always growing. Okay? Then, if it grows too much past that K line, then negative. Okay? Yeah. So this way to model that phenomenon. Okay? Up and down phenomenon. Yeah.
So it would look sinusoidal?
So,
It would theoretically look sinusoidal. It wouldn't be...
oh, not as perfect, because sinusoidal, it's perfect, right? This, some, yeah.
What I'm getting at is like with this equation, like it's not just a plug in once and you're done. You have to keep plugging.
Yeah. Yes. Yeah. Because it's a function of t. T is changing, right? Yeah. So keeps changing. Yeah. P as a function of t, keeps changing.
Right.
Yeah.
And this you're saying this also equation is also built on statistics.
Yeah. Based on so this model may not be perfect. Okay. When people make this model, so they try to compare with the real world statistics. If it fits well, then
So they try to make this equation model the statistics.
yes, yeah, that's the statistical data, using statistical data to adjust this model.
So like here the stat,
Yeah.
they want a differential equation to represent that.
Yes.
It'd be like, I don't know, maybe birth trend versus death trend
Better
in a
example
recent
is,
time or something.
you have wolves and they're feeding off the rabbits. They get to a point where there's no more rabbits, they die off and they...
Yes.
Oh,
Yeah.
sure.
Yeah. So that's because how people do the modeling, right? How people do the modeling. Okay? Yeah. Many times based on analysis. Okay? Yeah. Because nobody tells you this is the ODE. This is the right ODE. Nobody tells you, right? Yeah. So you need to create it. You need to make it. You as a problem solver, you need to make your own ODE to model the given problem. Okay? But how do you know it is correct or not? If you have real world data, so you use your real world statistic data to adjust your model. Okay? Yeah? So, yeah. If it fits quite well, yeah, then it's a good model. Okay? If not quite well, then you need to, try different ways. Do something here and there, try to make it, fit well. Yeah. Yeah. That's modeling. Yeah. Yeah. Because sometimes it's very hard to explain why you use this ODE, sometimes PDE. Why you use differential equations to this? Yeah. It's hard to explain. Yeah. Question.
Isn't this also based off of the interest formula? Or from,
What formula?
like, economic interest?
Oh,
Isn't it?
no. Yeah, that one, because that one is very restricted. Yeah, very restricted. So this model is more complicated than that one, right? Interest rate. Yeah. Interest rate, yeah, because keep going, right? Yeah. And that one actually, the formula for interest rate, you do not need to, because you know it is correct. Yeah. So it's not here. We need to use the real world data to tell us if it fits well or not. That interest rate, everyone knows that formula is correct. Okay? Yeah? Yeah. So that's different. So you can see the situation different. Yeah. Here, people may argue. Yeah. So, you can do better. Yeah. Sometimes people. So because if you are just here, if you do something else, people may argue. Yeah. You can do better. Yeah. A lot of arguments. Yeah. 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 So that happened. So in the real world, yeah, because when you solve real world engineering problems, you have the situation like this quite a lot. Yeah. Yeah. Because you need to make your own modeling equation. Yeah. Yeah. Good one, a bad one, so you need to do a lot of work. Yeah. All right? Yep. Okay. Next, some more discussion on popular dynamics. All right. Now, yeah, still this one, yeah, but model evolution population of plants, animals, human, yeah, yeah. So here, do some simple discussion, yeah, yeah. So that's why I said, so the first people use a simple modeling equation, okay? Simple modeling equation. So at the beginning, people do not use the negative b y squared term. So make it b 0. Yeah. So that's the initial modeling function. Okay. So the equation is y prime equals a times y, but this exponential increasing forever and no limit. Keep growing. Yeah. Yeah. But at the early time, Malthus law. Malthus law. Have you heard of that? A famous person who, in 50s, yeah, probably very early, in 50s, 40s, 50s, this guy, yeah, Malthus, this guy, used this modeling function. Too simple, yeah, not good. Yeah. But this law is only good for a small population in a large country. Okay, yeah, there is some restrict condition, small population. Okay, yeah, but in large area, so. That means under this condition, the population keeps growing. without any, stopping factor. Yeah, non-stopping growing. Yeah. Okay. All right. It takes exponential growth. So based on the Malthus law, the population takes exponential growth. Yeah. But that means at early stage, it's correct. At early stage, yeah. But sooner or later, not correct. Okay, not correct. Yeah, yeah. So then, when the population becomes sufficiently large, there must be a breaking term. This is the breaking term. Yeah. Okay, minus by squared. Okay, yeah. Breaking term. Okay, the larger the y, the larger the breaking term, right? The value. Yeah, because y squared. Okay, yeah. So the negative term grows much faster than the positive term, right? Positive term, yeah, look at the positive term, grows in a linear function, okay? The negative term grows in a square function, okay? So much, much faster. So the breaking, yeah, harder and harder, okay, to reduce the population. Yeah, this larger breaking term, yeah, is used to greatly reduce the population. That model. Yeah. Yeah. So that's pretty much true, right? So everyone here, you feel that, fits our real world phenomenon well, right? Yeah. 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 So if we write this way, yeah, 1 minus way, yeah, yeah, because 1 minus way, yeah, then it can tell us something. So we do the factorization on the right-hand side function in this way. All right, so we can draw a diagram. Draw this diagram. Yeah. Then now you can see there is a line, important line. Yeah. This, think about this term when b over a parenthesis times y equals 1. Okay. That line is critical, right? Yeah. That line is critical. Okay? Yeah. So this dashed line, that corresponds to that line. So that's the y equals a over b. Okay? Y equals a over b. Okay? So y times this parenthesis equals 1. Then y prime is 0. At this point, y prime is 0. The rate of change, 0. Yeah. Flat. Okay? Yeah. Yeah. All right. If y less than, so at the left-hand side of this line, left-hand side, y prime is positive. Y prime is positive, keep growing. Okay? Yeah. So the population function is an increasing function when y is less than this constant. Then at the right-hand side, when y is greater than this constant, then this parenthesis is negative. So the derivative is negative. So the population is decreasing. Okay? Y prime is negative, decreasing. So the population is decreasing, keep, smaller and smaller. Yeah? So that's the, interpretation. Yeah. So why people feel, so this model pretty good. Yeah. Because it reflects the, typical properties of the populations. Yeah. Yeah. All right. Yeah. Then autonomous ODE. Yeah. Another name So if you have this form, y prime equals f of y. Yeah. 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 So f function is a function of y, no x. You cannot see x. Yeah. So that's the autonomous ODE. Yeah. The logistic equation is a special case. You see, because no x. This f function, there is no x there. Okay? Yeah. So it's a special case of this type of ODE. Yeah. Then another concept, equilibrium solutions. Yeah. Equilibrium solutions here. Yeah. So when you look at the equation, the function here, think about when y equals 0. Okay? Y equals 0. This side is 0. So y prime. So when y equals a 0 function, okay? Yeah. Y is a 0 function. Then the population. So if at the beginning y is 0, then the population always 0, right? Yeah. Yeah. So that's one of the equilibrium points. One of the equilibrium points. Yeah. Because no change. Okay? Yeah. Another equilibrium point is y. Look at that. Y equals b over a over b. Constant. Y is this constant. Look at that. If y takes this constant, yeah, then y prime equals 0. Oh, no change, right? Yeah. So that's the second equilibrium point. Two equilibrium points here. Okay, all right. So constant solutions. Yeah. So when you consider equilibrium solutions, you consider the constant solutions. Y equals C solutions. Okay? If y equals C, then y prime is 0, right? Yeah. Constant, you take derivative, so y prime is 0. Then f of C equals 0, right? Yeah. So you can find C from the condition f of C equals 0. Yeah. So that is, you need to, in order to find these equilibrium points, you need to find zeros of f of y function. Okay? Yeah. 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 Also called the critical points of this equation. Yeah. I mean, just some, special names. Yeah. All right, so we complete this part. Yeah. Yeah. But we still have about 15 minutes. Yeah. Okay? Yeah. So I do not like to, waste this 15 minutes. So I may like to jump to module 2. Okay? Yeah. Because if we waste 15 minutes here and there, so that's quite a lot. Okay? Yeah. So let's go to module 2, even 15 minutes. Maybe we can do 1 or 2 slides. Yeah. Yeah, so this is the, module 2. Yeah. So let me, yeah. Okay. Oh, before we start module 2, let me give you just a minute. Let me give you some information about the homework assignments this week. Yeah, this week, because we complete the whole module 1. Yeah, so we need to do our first homework assignments for module 1. Yeah. 10 computation questions for this first homework assignments. Yeah. And because we have 5 parts in module 1, A, B, C, D, E, 5 parts. So I plan to do this way. Each part, 2 questions. Okay? Part 1, first 2 questions. Part 2, second 2 questions, and so on. Okay? So total 10 questions. Question?
Yeah, so for quiz 1, is that based on all of module 1, or is that based on, you might have covered this already, and I'm not remembering, but for quiz 1, is that like part A, what does quiz 1 cover?
Yeah, quiz 1 cover, so part A, part B, right? Yeah. Right? Yeah.
So the whole module 1? The entirety of module 1?
I've done most of it. I think it's pretty front loaded as far as the modules.
Okay.
Yes.
I
Yes.
haven't gotten to the last
Yeah. No, yeah.
Oh, so it's
So-
not timed it.
No, just up to that point. So when I assign you quiz 1,
Oh, it was
yeah, we already covered. I do not go ahead of the, I cover C, but at that time I didn't cover, so I never do that.
Homework 1 will just be on module 1.
Yeah, only homework 1 only on module 1. Okay, module 1. So 10 computation questions.
Since we're going to module 2 here, you're posting the homework 1 now?
Yeah, this weekend I will post. Yeah, this weekend. Okay? I haven't posted because I haven't compiled the questions.
Oh, no, yeah, that's okay.
Yeah.
That's okay.
Yeah.
I just want to know how much time we're going to have to complete it.
Yeah, oh, yeah. So usually I give you, longer than 1 week. Okay.
okay.
Yeah.
That's good.
10 days. Yeah. Between 10. Yeah. Minimum 10 days.
Thank you.
Yeah. I mean maximum 2 weeks. Yeah. Yeah. Or something between like 12 days. Yeah. Things like that.
Thank you.
Approximately. Yeah. So each question 6 points. So total 60 points. Yeah. So each part 2 questions. Okay. Yeah. Some of the questions word questions, but for some parts I may give you 1 word problem and 1 solving equation problem. Yeah. Because some part we need to solve equations, directly without, Yeah, so 1 word problem plus 1 equation problem. But first module, because solving equation too easy, right? So I will give you 2 word problems. Yeah. Some problems because equation solving part very easy. So then I will give you 2 word problems. If the equation solving part not very trivial, okay, there is some technique, okay, yeah. So you need to do some work. Yeah. For example. For the extended separable, that topic. So I will give you ODE problem because you need to find a way to make it separable, right? Yeah, you need to do some work to make it make it separable. Yeah, variable substitution, that's non-word problem. Yeah, things like that. Okay. Yeah. All right. Yeah. So then we start module 2. All right. Yeah. So let me just do 1 slide. Okay, 1 slide is good enough. Yeah. The title: Second Order Linear ODEs and Introduction to Laplace Transform. Okay, 2 topics. Yeah. And the Laplace transform very important. Yeah. So we will spend a lot of time on this topic, Laplace transform. Okay, yeah. So I put in the module 2. Yeah. All right. Second order ODE. Yeah. So we use 1 whole module to talk about second order ODE. Yeah. So there is some reason. Yeah. Most of the engineering problems use first order or second order. Most. Yeah. So, although pretty simple, but these two types of ODE cover most of the engineering problems. Okay, so that's why. So we need to, study this topic well. Yeah. All right. First, the simplest type. Second, simplest type, the homogeneous second order linear ODE. Yeah. Properties of second order linear ODEs. Yeah. All right. Yeah. Let's look at the definition. Yeah. Standard form. Yeah. Homogeneous. Okay, 0 here. Okay. Standard form of the linear homogeneous second order ODE. PQ function. Yeah. All right. First, let's study the linearity property. Here, this property is useful. Linearity property. Yeah. I mentioned a little bit before, but here we need to get a good understanding on this property. Linearity property. Yeah. All right. What do you mean here? How do you understand that this equation, a given second order ODE, is a linear ODE? Yeah. So we need to make that clear. Yeah. Yeah. So look at the description. Yeah. With respect to y double prime, it is a linear function. With respect to y double prime, yeah, it's a linear equation. That one condition. Yeah. All right. And the coefficients of y double prime. Yeah. So here we need to add, because this is still not very accurate. So we need to add more restriction. Okay. So this the coefficient of y double prime cannot contain y prime or y. Yeah. Yeah. Coefficient of y double prime can contain x. Yeah. It's okay. Contain x, no problem. But cannot be y prime or y. Yeah. Yeah. All right. With respect to y prime, it is a linear function. Okay? Yeah. But the coefficient of y prime cannot contain y double prime and y. Yeah. Okay? Yeah. All right. Otherwise, you cannot call linear. Okay? Yeah. Otherwise, you cannot call linear. For y also the same rule. Yeah. Linear, but the coefficient of y cannot contain y double prime or y prime. Now you can see, based on these three rules, it is a linear ODE, second order linear ODE. Okay? Yeah. Yeah. Here you can see, although here we are talking about second order linear ODE, we can generalize these rules to higher order ODEs, right? Yeah. Higher order, we can also use the, similar rules. Yeah. All right. Example. Yeah. First example, in this case, you can see it satisfied all these three rules. So it is linear ODE. Yeah. Homogeneous second order linear. Yeah. Yeah. So we can write a standard form in this way. Yeah. Standard form, yeah. So we want to make the coefficient of y double prime 1. Okay? Yeah. Y double prime 1. Yeah. 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 So but the second, we can see the coefficient of y double prime contains a y. Okay? And here there is a square. Okay? Yeah. Yeah. So it's not. Linear ODE, second order linear ODE. Yeah. All right. Yeah, very easy. So you can tell. Yeah. Then there is a question here. Why it is important to study the second order linear homogeneous ODE? Yeah. So here, yeah. Why we need to consider this special type of ODE? Yeah. The answer is very simple, because this type of ODE satisfies the linearity property. Okay? Yeah. If non-homogeneous, yeah. So if you have R function, non-zero R function at the right-hand side, then you do not have the linearity property. The next slide gives you a simple example about this question. Yeah. So we have 5 minutes. Let's look at that example. Next slide. Yeah, see this Y. All right. Superposition principle or linearity principle. Okay. Yeah. Same meaning, yeah, but people may call it in a different way. Superposition, this word appears quite often in our class, yeah, later. Yeah, linearity, yeah, so you know the meaning quickly. All right. Consider, yeah, assume. So here we want to check the linearity. What's linearity? Yeah, yeah. Show you the meaning of this linearity. Assume that y1 function and a y2 function are two solutions of the above ODE. Okay? So you can plug in y1, y2 into the original equation. So y1 satisfies the original equation. y2 also satisfies original equation. Now we want to do linear combinations of these two equalities. The first one, we multiply constant C1. Second one, we multiply constant C2, then add them up. What should we get? Yeah, we do some calculation. So we can put corresponding terms in the parentheses, right? Yeah, corresponding terms inside parentheses. Yeah, all right. Can you see? Yeah, when you do this, can you see inside the part inside parentheses? Inside parentheses. The same function, yeah, because the same function C1y1 plus C2y2, yeah, appear in these three pairs of parentheses. Can we treat it as one solution of this equation? Yeah, same function satisfy the original equation. So this equality tells us any linear combination, because we call this linear combination, right? C1y1 plus C2y2, we call linear combination. So the conclusion is any linear combination of y1 and y2 is also a solution of the above ODE. That's the meaning of linearity principle. So here we prove it. Yeah. This homogeneous linear second order ODE satisfies that linearity principle. Yeah? We prove it. Okay? All right. Yeah. So 2 more minutes. Let me show you something does not hold. This principle does not hold for non-linear. Because it's one. Non-homogeneous. Okay? Yeah. Non-homogeneous linear or non-linear. Yeah. Non-homogeneous. Yeah. All right. First, y1. You can easily see y1. This function, 1 plus cosine of x, double prime, you add them up, equals 1. So it's a solution, right? y1 is a solution. Okay? y2, 1 plus sine x. Double prime, negative sine x, adding together equals 1. So y2 also a solution. Okay, all right. Then, linear combination. Let's just add y1 plus y2 and see if it's a solution. Okay? So y3 equals y1 plus y2 equals 2 plus, yeah. Then, double prime of y3, constant gone, negative cosine, negative, cancel out. So this function satisfies double prime equals 2, not 1. So y3 is not a solution of the original ODE. y3. Okay? So this is a counterexample, right? Yeah. Linear combination of two solutions is not a new solution. For example, yeah, because it's non-homogeneous. Yeah. All right, yeah, let's stop right here. Yeah. Yeah. Next time we continue this topic.